Jupiter, the captivating gas titan, reigns supreme in our solar system. Its grandeur only dwarfed by the Sun. This colossal planet, with its mesmerizing bands and iconic Great Red Spot, stands as a testament to the universe's wonders. Yet, beneath its awe-inspiring facade lies a world of mystery. Despite its allure, Jupiter is unpredictable and hostile, with violent storms and intense radiation belts. While it serves as a beacon of fascination for astronomers and space enthusiasts, it also reminds us of the unpredictable and tumultuous nature of the cosmos. Let's embark on a journey to unravel the enigmas of Jupiter. Join us as we dive deep into the swirling clouds, explore the metallic oceans, and attempt to decode the planet's many mysteries. This voyage into the captivating world of Jupiter and its secrets that lie within begins. Often hailed as the most mysterious planet in our solar system, Jupiter is a treasure trove of oddities that have left scientists both intrigued and baffled for centuries. At its core, this gas giant is believed to harbor metallic oceans, vast seas of liquid hydrogen that exhibit metallic properties due to the immense pressures they're subjected to. Above these depths, the iconic Great Red Spot rages on, a tempestuous storm larger than Earth itself, which has been churning for at least 400 years, if not longer. The longevity and persistence of this storm are phenomena that remain largely unexplained. Despite the plethora of studies and missions dedicated to it, Jupiter continues to guard its secrets closely, often presenting more questions than answers. Its immense size, powerful magnetic fields, and complex atmospheric dynamics make it a unique subject of study, yet also one of the most challenging to understand. Jupiter, the behemoth of our solar system, is orbited by a staggering 95 moons as of March 2023. This number is a testament to both the planet's immense gravitational influence and the relentless pursuit of knowledge by astronomers. Over the years, as observational technology has advanced, from Galileo's rudimentary telescope to modern space-based observatories, our ability to detect smaller and more distant moons has improved. Each discovery adds a new piece to the puzzle of our solar system's formation and evolution. In comparison to other planets, Jupiter's collection of moons is unparalleled. Saturn, its closest competitor in terms of moon count, still lags behind. The sheer number of satellites around Jupiter is indicative of its massive gravitational pull, which acts as a cosmic net, capturing a wide array of celestial objects. Many of Jupiter's moons are believed to have been formed from the same solar nebula material from which the planet itself was born. These moons, primarily the four largest ones known as the Galilean moons, have been known since the early 17th century, when Galileo Galilei first observed them. However, a significant portion of Jupiter's moons, especially the outer and smaller ones, exhibit retrograde motion, suggesting a different origin. These moons likely did not form in place around Jupiter, but were captured by its gravity. They might have been asteroids, comets, or other celestial bodies that ventured too close to the gas giant and were ensnared by its gravitational might. The process of capturing these celestial wanderers is fascinating. As they approach Jupiter, interactions with the planet or its existing moons can lead to a loss of energy, causing these bodies to be trapped in orbit around the planet. Over time, some of these captured objects settled into retrograde orbits, moving in the opposite direction of Jupiter's rotation. This phenomenon underscores the dynamic and intricate nature of Jupiter's satellite system and hints at the planet's tumultuous past. The giant is often referred to as the solar system's sentinel, playing a crucial role in safeguarding Earth from potential celestial threats. Its immense size and powerful gravitational pull act as a cosmic shield, deflecting or capturing space debris that might otherwise pose a threat to our planet. Some scientists believe that during the early days of the solar system, Jupiter's gravitational influence prevented many space rocks from colliding with Earth, allowing life to flourish without frequent catastrophic interruptions. Furthermore, Jupiter's gravity has played a pivotal role in shaping the structure of our solar system as an entirety. One of the most notable impacts of its gravitational might is the formation of the asteroid belt. Instead of allowing space rocks to coalesce into a planet between Mars and Jupiter, the gas giant's gravitational forces kept these rocks apart, leading to the creation of this asteroid belt. Recent discoveries, such as those from the Juno spacecraft, have provided insights into Jupiter's internal structure and dynamics, further emphasizing its influential role. In essence, Jupiter's protective nature, both in shielding Earth and in sculpting the solar system's architecture, underscores its indispensable role in the cosmic dance that has allowed life to thrive on our blue planet. However, science is never this simple. Recent scientific studies have begun to challenge the long-held belief that Jupiter solely acts as Earth's celestial protector. While its immense gravitational pull does capture or deflect a significant number of space debris, it may also be responsible for altering the trajectories of certain asteroids, making them potential threats to Earth. A study published in the Astrophysical Journal in 2020 highlighted this dual role of Jupiter. Using computer simulations, researchers found that the gas giant's gravitational influence can perturb the orbits of asteroids in the Centaur group, which lie between Jupiter and Neptune. Over time, these perturbations can cause some of these space rocks to be flung towards the inner solar system, accelerating them in the direction of the Sun. As these asteroids approach the inner solar system, their chances of crossing Earth's orbit and potentially colliding with our planet increase. This revelation underscores the dynamic and intricate nature of our solar system, where celestial bodies constantly influence each other's movements. While Jupiter remains a significant shield, deflecting many potential threats, it also plays a role in redirecting others towards us. There's a really good example of this. By the way, are you enjoying this video? Do us a favor and hit that like button. Also, be sure to subscribe and tap the bell icon so you never miss out on any of our brilliant content. You're officially an explorer now. A 1770 comet, also known as Lexell's comet, holds the distinction of being the comet that passed closest to Earth in recorded history. Discovered by Charles Messier in June 1770, it made its closest approach on July 1st of the same year, coming within a mere 1.4 million miles, or 2.2 million kilometers of our planet. To put this in perspective, that's roughly 6 times the distance between Earth and the Moon. Scientists believe that Jupiter played a significant role in directing this comet towards Earth. Prior to its close encounter with our planet, Lexell's comet had been gravitationally perturbed by Jupiter in 1767, altering its original orbit. This interaction with the gas giant set the comet on a trajectory that would eventually bring it alarmingly close to Earth. However, the story of Lexell's comet doesn't end with its 1770 appearance. After its close pass by Earth, the comet's orbit was once again modified. Then, in the subsequent years, it had additional close encounters with Jupiter. These gravitational interactions with the gas giant changed the comet's orbit so much that it was ejected from the inner solar system. As a result, Lexell's comet has not been observed since its appearances in the 1770s, and its current whereabouts remain unknown. Understanding space rocks from the asteroid belt is a very important study. In many cases, they are the key to different elements becoming part of a planet. As human beings, our biggest interest is in finding the presence of water. The quest to detect water on Jupiter has been a significant focus for astronomers, given the implications it holds for understanding the planet's formation and the history of our solar system. In 1995, the Galileo spacecraft dropped a probe into Jupiter's atmosphere, aiming to measure its composition. While the probe did detect water, it entered an unusually dry spot, leading to inconclusive results about the planet's overall water abundance. A breakthrough came with the Juno spacecraft, which began orbiting Jupiter in 2016. Using its microwave radiometer, Juno detected water vapor in the planet's atmosphere. Data from Juno suggests that water makes up about 0.25% of the molecules in Jupiter's atmosphere at the equator. This is several times the amount of water present in the Sun, which, in case you didn't know, does in fact show the presence of water as well, indicating that Jupiter likely formed farther out in the solar system before migrating inwards. In comparison to Earth, where water covers about 71% of the surface, Jupiter's water content is minuscule. However, given Jupiter's massive size, even this small percentage translates to a vast amount of water, likely many times the Earth's total volume. On Jupiter, water plays a crucial role in driving its atmospheric dynamics. The presence of water affects the planet's cloud formations and can influence the generation and propagation of massive storms like the Great Red Spot. Understanding Jupiter's water content is not just about the molecule itself, but about piecing together the broader puzzle of our solar system's evolution and the mysteries of this gas giant. Its atmosphere is a hotbed of meteorological activity, with lightning and rain being among its most fascinating phenomena. The planet's lightning, first detected by the Voyager spacecraft in 1979, is similar in nature to Earth's, but occurs much more frequently and can be thousands of times more powerful. These electrical discharges are believed to originate from the planet's deep water clouds, located about 50 kilometers below the visible ammonia clouds. The rain on Jupiter isn't like the familiar water droplets on Earth. Instead, it's believed to be made of liquid helium or neon. As the planet's interior heats up, helium or neon dissolves in the raindrops, causing them to fall towards the deeper layers. This process was supported by data from the Galileo probe. Moreover, recent observations from the Juno spacecraft suggest the presence of mushball rain, a slushy mixture of water and ammonia. These mushballs form in the deep atmosphere, encapsulating water droplets and carrying them into the deeper layers, playing a significant role in Jupiter's atmospheric dynamics and chemistry. This unique precipitation offers a glimpse into the complex and alien meteorology of this gas titan. The thick and complex atmosphere has been a subject of intrigue for astronomers and scientists. Dominated primarily by hydrogen and helium, this atmosphere showcases a vivid tapestry of colors, bands, and tumultuous storms, offering a window into the planet's intricate meteorological dynamics. At the outermost region, where the most visually captivating features reside, alternating bands of light and dark can be observed. These bands are manifestations of rising and sinking air, with the lighter bands being regions of high-altitude clouds and the darker ones representing deeper cloud layers. Within this region, one can also spot the iconic Great Red Spot, a massive storm larger than Earth that has raged for centuries. As one delves deeper, the atmosphere becomes warmer, containing thin clouds of hydrocarbons. These are formed due to the interaction of ultraviolet sunlight with methane, giving rise to a variety of complex molecules. Further down, where the atmospheric pressure intensifies, brilliant auroras emerge. These dazzling light displays, much like Earth's northern and southern lights, result from charged particles colliding with the planet's gases. Deeper still, beneath the visible cloud layers, the environment becomes increasingly hostile. Here, the pressure and temperature rise so steeply that hydrogen, the primary constituent of Jupiter's atmosphere, undergoes a remarkable transformation. Subjected to these extreme conditions, hydrogen transitions into a metallic state, exhibiting properties of both a liquid and a metal. This deep layer is believed to be responsible for generating Jupiter's powerful magnetic field. In some ways, Jupiter is also very similar to Earth, but just on a larger scale. Jupiter's magnetic field is one of the most formidable and intriguing phenomena in our solar system. It's the strongest planetary magnetic field known, approximately 20,000 times more powerful than Earth's. This immense magnetic cocoon, extending millions of kilometers into space, is generated deep within the planet's core, where the pressure is so intense that hydrogen, the primary constituent of Jupiter, transitions into a metallic state. This metallic hydrogen, with its free-moving electrons, acts as a dynamo, generating the magnetic field as the planet rotates. One of the most captivating manifestations of Jupiter's magnetic field is its auroras, which are the most powerful in the solar system. These shimmering light displays, primarily concentrated at the poles, are created when charged particles, accelerated by the planet's magnetic field, collide with its atmosphere. The interaction results in brilliant bursts of light, much like the northern and southern lights on Earth, but on a grander scale. A particularly intriguing feature associated with Jupiter's magnetic field is the Great Blue Spot, a lesser-known cousin to the more famous Great Red Spot. Discovered using data from NASA's Juno spacecraft, the Great Blue Spot is an ultraviolet aurora, not visible to the naked eye, located near the planet's equator. Unlike the Great Red Spot, which is a massive storm system, the Great Blue Spot is directly tied to the planet's magnetic field. It represents a region where the magnetic field lines are particularly strong and densely packed, leading to intense auroral activity. Comparatively, the Great Red Spot is a colossal, high-pressure anticyclonic storm that has persisted for at least 400 years. Its reddish hue, still a subject of scientific debate, contrasts with the blue of the magnetic hotspot. While the Great Red Spot is driven by atmospheric dynamics, the Great Blue Spot's existence is intrinsically linked to the underlying magnetic processes. Interestingly enough, the Great Red Spot and the Great Blue Spot, while distinct in nature and origin, may have an intriguing connection. Recent studies, particularly those utilizing data from NASA's Juno spacecraft, have suggested that the two spots might be linked through magnetic field lines. The Great Blue Spot, an intense region of magnetic activity near Jupiter's equator, lies almost directly north of the Great Red Spot. Some scientists speculate that the magnetic forces from the Great Blue Spot could influence the atmospheric dynamics of the Great Red Spot. The proximity of the two features and their alignment along a magnetic field line provides compelling evidence for this potential connection. While the Great Red Spot is a massive atmospheric storm, the magnetic forces from the Great Blue Spot might play a role in sustaining or influencing its longevity and behavior. Further studies and observations are needed to fully understand this intricate relationship between Jupiter's atmospheric and magnetic phenomena. But this isn't the end for such anomalies. The Great Cold Spot on Jupiter is a relatively recent discovery that adds another layer of complexity to our understanding of the gas giant. Unlike the iconic Great Red Spot, the Great Cold Spot is characterized by its temperature. Located in Jupiter's thermosphere, it's about 200 degrees Celsius cooler than the surrounding atmosphere, making it a vast region of cooling amidst an otherwise hot upper atmosphere. This cold spot is believed to be directly related to Jupiter's powerful auroras. The planet's auroras are the most intense in the solar system, generated by charged particles colliding with the atmosphere under the influence of its strong magnetic field. These auroras produce energy, which heats the surrounding atmosphere. However, the Great Cold Spot appears to be a region where cooling due to auroral activity dominates overheating. The energy from the auroras creates a localized cooling effect, leading to the formation of this cold spot. Jupiter's auroras, much like Earth's northern and southern lights, are a manifestation of the interaction between a planet's magnetic field and the solar wind. However, the scale and intensity of Jupiter's auroras far exceed those on Earth. For instance, while Earth's auroras are primarily driven by the solar wind, Jupiter's are also fueled by charged particles ejected from its moon, Io, leading to more frequent and powerful displays. A study published in the journal Nature in 2017 highlighted the discovery of the Great Cold Spot and its potential connection to the planet's auroras. The research emphasized the dynamic nature of this cold spot, which appears to change in size and shape over time, yet has remained present for at least 15 years based on observational data. But Jupiter has one more trick up its sleeve, something similar to other planets, however more apparent. Jupiter's orbit around the Sun presents a captivating celestial dynamic. While it's commonly believed that planets orbit the Sun's center, in reality, they orbit a shared center of mass called the barycenter. Due to Jupiter's immense mass, the barycenter for the Jupiter-Sun system lies just outside the Sun's surface. This means that while Jupiter orbits this point, the Sun also exhibits a slight wobble around it, rather than remaining stationary. This phenomenon isn't exclusive to Jupiter. All planets, including Earth, have their own barycenters with the Sun. However, for planets with significantly lesser mass than Jupiter, the barycenter is much closer to the Sun's center. For instance, Earth's barycenter with the Sun lies within the Sun itself, making its effect less noticeable than Jupiter's. A study utilizing data from NASA's missions has detailed these orbital dynamics, emphasizing the mutual gravitational influences celestial bodies exert on each other. This understanding challenges the traditional notion of orbits, revealing the intricate gravitational ballet that shapes the movements of our solar system's members. In essence, the dance of planets around the Sun is more collaborative than previously thought, with each planet influencing the Sun's position in a delicate balance of gravitational forces. Enjoyed the video? Make sure you subscribe and be sure to check out more of this top content from our channel. See you soon, explorers.